Array is nothing but it is collection of similar data type. If I want to sort integer, I have to take which array? Integer array. Once we get the solution, it's time to combine. Why we combine? If you don't combine, we don't get the output for the original input. So when we think about space complexity, when we think about the memory space, divide and conquer takes much space compared to which decrease and conquer. Hello everyone, myself Evelyn Jacob, working as a faculty in BCA department, Vidhyaashram First Grade College, Temple of Excellence, Mysuru. So today's session we are discussing about the subject Design and Analysis of Algorithm. That is, in the Unit 4, we have a chapter Decrease and Conquer. So in this unit, we'll discuss about the algorithm and how to solve and what are the problems regarding the algorithm. So the very first introduction is decrease and conquer. What do you mean by decrease and conquer? So decrease we already know it is reducing. Then what about conquer? Conquer is nothing but solving the problem. So it is a strategy involving solving the problem. How to solve? First we have to reduce. That is what is called decrease. And when we decrease, we get a smaller input. When there is n number of input, we decrease say n by 2. Then we have to solve. So it is type of a algorithm which will make us to simplify. So what are the steps involved? If we understood what is decrease and conquer, now it is the time to see the steps. See, decrease we discussed that we'll reduce the problem size. So then we'll conquer. Conquer is nothing but to solve the problem. How to solve? We have decreased. So the problem is smaller for us. Then after we solve, that is conquer, we will combine if needed. If needed, we have to combine the solution of the smaller instance, a smaller problem, so that we can solve the original problem. So original problem is given, we have reduced, that is we have decreased, and then we conquer. Conquer is nothing but solve the problem. So in the decrease and conquer, we have one example of sorting, that is nothing but insertion sort. When we discuss about sorting, is nothing but arrangement of elements, usually in ascending order. It can be descending order also. We prefer ascending order. So input is unsorted, or it can be sorted also. What is the output? We should get a sorted. So what is insertion sort? The term insert. So we are inserting into appropriate place. If my element is smaller, make the element to come at the beginning. So we discuss about insertion sort. So we say insertion sort, it is very simple. It is a sorting algorithm. It sort a section of the array. So if I want to sort, it should be array. Array is nothing but it is collection of similar data type. If I want to sort integer, I have to take which array? Integer array. So what is the idea behind insertion sort? We'll divide the array into two parts. So that is, we are decreasing. Then what we do is, the algorithm repeatedly takes an element from the unsorted part. So element will be taken from the unsorted part. As the name itself tells, it is insert. Make it insert in its appropriate position. That we say correct position within the array. So how to take it? Which element to be inserted? That is, first is initial state. Initially, elements will be given. We prefer the first element in the array is sorted. So there are 5 elements, say 10, 20, 30, 40. So we prefer 10 is already sorted. That is what? That is initial state. Then it is iteration. Because there are many elements, say 5 elements, I have to do iteration one after the other. So it iterates through the unsorted part. Suppose if you are given the unsorted, it will come on doing the iteration. Starting from the second element. Why second element? The first element we have considered it as sorted. Now we'll compare the first element with the second element. Then comes the insertion. First is initial state. Next was the iteration. Now the process of insertion starts. For each element in the unsorted part. So we'll consider the second element. Then what will happen is, it keeps shifting the elements. Why it is shifting? To make it in the ascending order. To make it in the sorted, we keep on shifting. Then, until where we have to shift? Until it reaches the correct position. So, this is iteration. In that, we do insertion after the iteration. Then repeat. Until where we have to repeat? Until all elements are sorted. If I give 10, 20, 30, 40, it's already sorted, but still it checks whether it is sorted. So if I give something jumbled up like 40, 20, 10, 0 and all, that time this proper aspect will happen. So this is repeating. So we'll go to the algorithm. What are the steps? We discussed about the procedure. Now it's the steps to be taken. Again, it is repeated. If the element is the first element, assume it is already sorted. We already discussed in our initial state. Then step 2. What we have to do in step 2? Pick the next element and store it separately. So second element is picked. Store it separately in a key. Why we have to store? That is the third step there. What is the third step? We have to compare the key with all elements. Now it's time. We have kept the second element separately so that we'll compare with all the elements. What about step 4? Now we have to compare whether that is greater or lesser. That is step 4. If the element is sorted array is smaller, then smaller, nothing to do, right? So then the current element, then move to the next element. So we will move to the next element. Else shift greater element in the array towards right. We always know greater element towards right and left will have the smaller element. So now we have to insert the value depending upon the condition. Last step is repeat until the array is sorted. How we know until the array is sorted? Until the elements are there, we keep on iterating. So at last we'll get a sorted array. Next, see, we know the steps in insertion, but how much time will it take to execute? So we'll determine using the complexity. That is time complexity. We already discussed this in our unit 2. The best case, average case, worst case. Best is we consider a symbol. This is all big O, right? It is asymptotic notation. So what we do is, in the best case, we prefer that it may be already sorted. So we just check it. We don't want to insert into appropriate position because array is already sorted. So the best case will be big O of n. What is n here? N is the size of the input, say size of the array. So what about average and worst case? We always give example for average cases. Half of the sorted elements are inserted correctly and half we have to sort. In worst case, it is all unsorted. We have not given a sorted array as an input. It is jumbled up. So even though this is, say, half of it is sorted, this is fully we have to sort, but both this have same complexity. We assume that it is big O of n square because 2 times. One is we have comparing the elements and we have to shift to appropriate position, meaning to say insertion is done. So it is double n square. See, here it is n, whereas for average case and worst case, it is n square. So how it occurs? Here is a description for it. It occurs when there is no sorting required. We already discussed this in our best case. Then, how is the average case? It occurs when the array elements are in jumbled order, that is not properly ascending. Our input is not in ascending order, it is jumbled up. So that is where you have average case. And worst case occurs when the array elements are required to be sorted in reverse order. So sometimes we may give in descending order. So our sorting output will be in ascending. When the insertion sort is done, we'll go for the topological sorting. When we see topological sorting, we see a graph, right? This topological sorting takes a directed graph. When I want to do a topological sorting, see, topological sorting graph will be given. According to the graph, we have to sort. So input is a graph, output will be the order of this vertices. Okay. Now what we have to do is, we have to consider it should be directed. See, if I give an arrow mark like this, you can see this arrow mark. All this arrow mark tells you direction is given. Suppose if I write something like this, there is no arrow mark, we say undirected. So how to do this topological sorting? So what it tells is, the ordering of the nodes in the array is called topological ordering. We will order the nodes, say 1, 2, 3, 4, 5 are the nodes, or we can say it is vertices, and the lines which are connecting are called edges. Okay, this is topological sorting. Next, how to do the topological sorting then? I know if I give an elements like 5, 4, 2, 3, 1 something, I do arrange like 1, 2, 3, 4, 5. But what about this? My input is a graph. How to consider this? So, first we have to see the very first node, say node 1. See, here is explanation. Node 1 points to node 2 and node 3. See, from node 1, I can go to node 2 and also node 3. So, node 1 appears before them in the ordering. So, if I want to write in the order, since I have an edge from 1 to 2 and 1 to 3, how to write the sorting? First, I have to write this node 1. Then from where it comes the node, that is 2 and 3, it is followed. Okay. So, you can see this. See 1, from 1 it comes to 2, 3. From 3 you can go to 4. See, from 3 you have a edge to 4. So, again from 1 is also 3 is coming. Then, so this tells 1, 2, 3 is already sorted. But for 4, what has happening? From 2, there is a edge, right? Then, from 4, direct one edge is there to 5. So, the order you have to mention, that is sorting. See, so 1, 2, 3, 4, 5 would be a topological order. Why I did not take any other vertices before 1 is, so 1 is the initial vertex here. Whatever nodes will come, I have to write it down. So, a graph can have more than one valid topological sorting. So, you can write other topological sorting also. How it is? 1, 3, 2, 4, 5. According to us, it is not sorting. How come 1? 1 is there. Okay, 1 is first number, it's correct. But this is 3 and 2. But according to this graph, it is correct, right? So, 1 is there. 1 is the first one and followed by 3. Why 3 means 1 is connected to 2 and 3. So, I can take 3 also first, or according to this, I can take 2 also. So, both are correct. Next comes the divide and conquer. See, decrease, we are reducing the problem. Divide. First we'll divide, then what will happen? The subproblems will be there. We have to solve it, then combine. So, divide and conquer, combine to get the solution to the original problem. So, what exactly is divide and conquer? What's the difference? So, divide and conquer is an algorithm pattern. Even decrease and conquer is also an algorithm, right? So, design is to take a dispute on a huge input. So, we'll take huge input, say 20, 30, 100. That is huge input for us. In your lab, how much number will you give? Say 5 or 6. But for this, in order to divide, it can be huge. Otherwise, no need to divide, right? Then, it is broken into minor pieces. Means break down into smaller problems. Then decide the problem on each of the smaller pieces and then merge the solution into a global solution. Why we divide is so that it can be solved and then combined to the global solution, means original solution. So what are the steps involved in divide and conquer? So very first step, the name itself tell divide. Divide the original problem into set of subproblems. So original problem is divided into how many? A set. It can be more than one, right? Then conquer. Conquer means solve. How to solve? It solves the subproblem individually, recursively, calling again and again. We already discussed recursive function. So divide is over, solving is over, and then we have to combine. If we don't combine, we don't get the output or the solution to the original problem. So put together the solution to the sub-problem so that we get the solution to where? To the global solution. So what and all we discuss, it's nothing but this diagram only. When we see this diagram, we can give the explanation. First, we have given a problem, say any problem. We discuss about, say, merge sort. Merge sort. So the input is divided. How many problems? Say they are given 2 subproblems. So left will be there in the subproblem and right of the array will be in another subproblem. Then what we have to do? We have to conquer. Conquer means is nothing but solve. Here also we have solved the subproblem. Once we solve, we get a solution. This is the solution of first subproblem. This is the second subproblem or the right side of the subproblem. Once we get the solution, it's time to combine. Why we combine? If we don't combine, we don't get the output for the original input. We have to combine so that the solution to the original problem is achieved. So this is the diagram for what? Divide and conquer. So we already discussed between decrease and conquer. But we had also one more concept, divide and conquer. So what is this? What is the major difference? When we say decrease and conquer, we come to the definition. What we do is reduce the problem into simple, smaller problems. When once it is reduced, recursively, we combine its solution. We combine the solution to address for what? For the original problem. Then what about divide and conquer? It is divide. See, here we say divide, here we say reduce. See the difference of it. Decrease is reduce, divide is divide only. Divide the problem into smaller problem. So we get what? Independent subproblem. Then after we get independent subproblem, we'll combine the solution to get what? Original solution. Next, what is the next difference? See, decrease and conquer involves the problem into a series of steps. So each reducing the problem, so we have to reduce the problem, so we are doing decrease and conquer. Why we are doing that? To express in terms of time complexity. So the time is reduced because we are reducing the problem. What about divide and conquer? It frequently employs the recursively calls. So recursive calls will be there and contains, you're gonna add that function. What is recursion? Calling itself within that function. So how it is done? It is done by recursively. So here also we'll express what? Its time complexity by divide and conquer. Then, so in decrease and conquer, recursive approach is done for what? First we find out the time complexity. Now we have to find the space complexity. What is space? The memory occupied. Here you have one more point. This is lower. Which is lower? It takes less space. Decrease and conquer combined to divide and conquer. Why is? We are reducing the problem, so we get less space. Less input is there. Whereas divide and conquer will take higher space. So when we think about space complexity, when we think about the memory space, divide and conquer takes much space compared to which decrease and conquer. See, because we have already reduced the problem, now the size is less. But here we divide it, but we are not reducing. Divide, conquer means solve and then combine. So you can imagine the memory space of it. So what is the example for decrease and conquer, what we have discussed in this session? It is insertion sort, topological sort. What about examples of divide and conquer where we discuss now? It is merge sort and quick sort. These are the difference between decrease and conquer and divide and conquer. So we told what are the example for divide and conquer? It is merge sort. We'll discuss here. The name itself tells merge. What is merge? Combine. Now how we divide this sort, merge sort, and we'll combine the solution. So the final output will be a sorted array. Merge sort algorithm is follows divide and conquer. So who devised it? It was devised by John von Neumann in the year 1945. So how the procedure starts? First we'll divide. We have given what list? Unsorted or sorted? We'll think we had given a unsorted list. So we'll divide into two parts, right? So this step is performed recursively until each sublist contains one element. Until how much we have to divide? Until we get only one element. That is called sublist. At this point, the single element are considered as sorted. Anyhow, we'll divide into last single element. That single element is sorted. But still we have to combine to get the sorted one. So next is conquer. How to solve? It is then merged. Which is merged? The sublists are merged such that the resulting merging is sorted. So the list will be sorted. In such a way, we have to solve it. So until where it is repeated? Until there is only one sorted list. Until then, you have to repeat this procedure of conquer. Next, merge operation. So we have already conquered, we have already solved the divided portions, say left subarray and right array. So now we have to merge. Until we merge, we don't get solution to the original problem. So key operation is merge sort, that is merging step. So the name it's called merge. What we do in this, there will be two sorted sublists. So the two sorted will be then again compared and then the final merging sort is done. So this process is repeated until the elements are merged into single. So last, if we don't merge, we don't get the final output. That is, we don't get the final sorted array. So step 1. We have already discussed here, but regarding the steps, we'll discuss again. So if it is only one element, that is already sorted. If your input is say 20, what to sort? 20 is already sorted. So we'll return that number. Next, step 2. If you add a number more than 1, then it is the process of dividing. Divide the list recursively into two halves. Recursively means continuously you should divide. So until where you should divide is until further you cannot divide. Until then keep on dividing. Next, merge the smaller list into new list. Whatever we have divided, we have to merge the smaller list. Into where? Into new list. So we call a merge sort. Here is the small code for the merge sort. What is the merge sort? It is the name of the, here we can say algorithm or the name of the function. So what is this? This is an array. What is beginning? Say we can say it is a low, first index. What is end here? It is the last index. We always check a condition. If beginning is less than end, means if there is more than one element, this is absolutely correct. It will be 5 element. So if it starts with 0, I can check 0 is less than 4. Why 4? It is n minus 1. So 0 less than 4, then this step will continue. If I give only one element, if 1 is less than 1, My beginning also 1 and end is also 1. Is 1 is less than 1? No, 1 is equal to 1. So it will come out of this loop. So if this condition satisfies, what is the statements to be executed? First I have to find out middle. MID is nothing but middle. So beginning plus end divided by 2. What is my beginning here? It is 0. What is my end? 0 plus 4. 4 divided by 2 is nothing but 2. So depending on the mid, we have divided now. So we have calling the merge sort. So merge sort is not a predefined, we have to write the code for it. So a merge sort, if you write the code in a C program separately, depending on that, we have to implement. So merge sort, it is an array beginning, middle. Now middle is how much? 2. What is beginning? 0. So it is divided. The left, this is the left array and this is the right array. And what about the right array? Again we are calling merge sort. What are the parameters passed? It is an array middle plus 1. What is middle? 2. 2 plus 1 is 3. So middle will be 3. What is my end? End is same. It is 4. Suppose I give 5 elements. So these two processes will do the sorting of the left and right array. After sorting, it's time to merge. So merge and we should get a final result. For that, we have to pass the array beginning, middle, end. So how many parameters are there? 4 parameters. So once the merge sort is done, why we do all this sorting, all these algorithms? To analyze its complexity. So what is the time complexity? See, when you just remember that whenever divide is there, the complexity will be high. Why? We have to take the input, divide, left and right will be there, solve left, then again you have to solve the right one and combine so that the procedure is there. So in the best case, what we say, it is big O, n log n. Why it is n log n? So divide procedure takes some more steps. So we always prefer with the log. The best time complexity of merge sort is big O of n log n. Why this occurs is when the input array is already sorted or nearly sorted. So if it is sorted or nearly sorted, we have to follow this procedure, divide and conquer. So we say it is n log n. So even in the best case, merge sort divides in the array into halves. What we discuss is this explanation. Again, we have to sort them, and so the time complexity is for best case also, it is more. Then what about average case? Same procedure. Even it is best, average or worst, the complexity never changes because the procedure is same for all. So merge sort has an average case big O of n log n. So the algorithm consistently divides the array into halves, means half, and merges them in sorted manner, maintaining the time complexity is same. So whenever we think about merge sort, this is the complexity regarding whatever cases it may be, best case, average case, and even the worst case. So no changes. For y'all it is easy to remember. So worst time case complexity of merge sort is what? Big O of n log n. Why same for worst case also? Again we have to follow the what procedure? The divide and conquer. See, we say that if the input array is in reverse order or completely unsorted. Worst is something like if it is not sorted or it is in descending order, right? That is worst case. So merge sort still efficiently divides the array into two halves and sort them, and result will be the sorted array. So the merge sort is consistent big O of n log n time complexity across the different cases. But we already know that if for 3 cases, this is the time complexity. And what is the space complexity? What do you mean by space complexity? Space is the memory taken by this program. Which program? Merge sort. It is big O of n. See, here we don't take log n. Why we don't take log n? See, what is the space? How much space I need for merge sort? See, my array is of 100 numbers. So 100 numbers is divided, right? So how much should I store? I should store this 100 numbers, that is n. N is nothing but input size. That is the space complexity of merge sort. Next comes the quick sort algorithm. Names tells quick. What is quick? Fast. So according to all the algorithm, we say quick sort is the fastest algorithm. How is this procedure? Again, it follows which method? Divide and conquer. Since we are in the divide and conquer, we already finished merge sort. Now we are in the quick sort. So it was developed by Tony Hoare in 1960. So it was developed by this person, Tony, in 1960. So he told this efficiency is better compared to other sorting algorithms. How this works? What is the explanation of it? As you know, it is divide, so we say partition. We can say divide or partitioning. So the main idea of the quick sort is to partition the array into smaller subarrays. Again, same concept, we have to divide. But it is not similar to merge sort, something extra is added. What is that? So what we do is, we take a pivot. We'll take maybe first element as pivot or middle element as pivot or the last element. Now we have to compare our pivot with all the elements and match if pivot is lesser or greater. This is about quick sort. When I say quick sort, remember the pivot. Pivot is nothing but a name given to the element. So the choice of the pivot can affect the performance of the algorithm, whether taking first one or the middle or last. Based upon that, your performance of the algorithm is decided. So how to select the pivot element? Commonly we use the first element. Say if there is 5 elements, say 10 is the first element, 10 can be pivot. Or sometimes in the middle of the program, the pivot can change. It may be the middle, say 30. And if suppose I reach to the last step of it, so the pivot will be last, or any random element also. So partition is done and my pivot is fixed. Then it is recursion. What is recursion? Recursion, we know that first we partition the array, that is array is divided into 2 subarrays, right? The quicksort algorithm is then recursively applied. Why it is applied? Now we have to do sorting, right? For the left and right. So the partitioning step is crucial, means it is difficult for the efficiency of the algorithm. So if it is more elements, it takes time. So the pivot also decides the performance of the algorithm. So quicksort tends to perform well if it is equally divided. Third one is base case. So the recursion continues until the base case is reached. So where a subarray has 0 or 1 element. So what is base case is when you give only one element or no elements. That is the base of it. So we decide the subarray is already sorted and how the algorithm works. See, here you have a quick sort, and in quick sort we usually give a array. So we say A is an array and this is start end. So start is my 0 index, end is my n index. If it is 5, n minus 1 is 4. Every time we have to check the condition. So why we have to check the condition? I have to give more than one element. I should never give 0 elements. If 0 or 1 element, this will not happen. For that we have to check what? The condition. So each time we'll partition this array with the start and end. So we'll get an element, say P. And each time after the partition has happened, we'll call the quick sort. We have discussed this, right? This is for the left subarray and last is for right subarray. So quick sort is array and the start P minus 1. See, P I got through partition. P minus 1 is something towards the left. Here the P plus 1 is there, right? It is right of it. So now what are the steps required? We just gone through the algorithm, a simple code of it. So the very first step is, if the length of the array is 0 or 1. So we have checked the condition. The very if condition was there, right? So return array is already sorted. If one element is there, that is sorted. Next, I have to choose my pivot element. How to choose? I prefer this choice can significantly affect the algorithm efficiency. So usually in your textbook, our pivot is in the first element. Next, partition the array into two subarrays. That is, element should be less than the pivot. If I take a pivot, say 10, 10 should be less than the left part, and the right part, if I contain, 10 should be greater than the right part. So element less than the pivot, that is left subarray. The elements greater than the pivot, that is what we call right subarray. That is simple as sorting. So recursively we apply quick sort. See, there we have called 2 times the quick sort. One for the left and another for the right. So this is left is over. Next step, we call a quick sort method for the right subarray. So we have sorted left and right. Now we have to merge. Merge means we say concatenate. Join them. Join the sorted left and right. So we'll get, when we join, we'll get what? Final sorted array. So when we come to the time complexity, what is the time complexity? Here also same thing as we discussed in our merge sort. N log n. When I say divide, it is something represented with log. So on an average case, quick sort performs very well as the time complexity is big of n log n. What about best case? Best case also same. So then what explanation will give for best case? So it is also big of n log n, which occurs when the pivot selection consistently leads to well-balanced partition. We have taken a pivot element such that the partition is well-balanced. The divide approach is good. So we always say the pivot element depends the performance. So pivot element is chosen as the median element or a random element. Randomly means anywhere. You can pick from the first, last or the middle or somewhere. We usually say random element, but we prefer pivot element to be the first element in your first line of the program. So worst case is big O of n square. See, in the worst case, time complexity of quick sort is big O of n square. Why is this so? When the pivot selection consistently result in highly unbalanced partition. By pivot, we are not able to do the partition. So we say highly unbalanced. So for example, I already discussed this. See, pivot is always chosen as first or last element if suppose my pivot is first or say last. So what happens? Then the input array is already sorted or nearly sorted, means half of it sorted or fully sorted. Each partitioning step may result only one element being placed in the correct position. So we don't need to do the sorting for the entire thing because half is sorted or already sorted. We say only one element being placed in where? In the correct or appropriate position. So the factors influence the time complexity. Even though quicksort is quick, we say it is pivot selection. The choice of the pivot significantly influences the efficiency of the quicksort. So how the partition is done is, the efficiency of the partitioning step can also impact the overall performance. This is dependent on the pivot. So the pivot can be first or last, or as I said, it can be randomly selected. Next, what is the average case efficiency? If the quicksort is often favored for its average case, what is the time complexity? Is compared to other sorting algorithms. So what are the other sorting algorithms? It's like bubble sort or insertion sort. But practically speaking, in practice, quicksort is widely used algorithm compared to other, what we discussed is selection sort, bubble sort, insertion sort. Other than this, quick sort is efficient. While quick sort has a worst case time complexity of big O of n square. So worst case we say big O of n square. What about the average case? It is big O of n log n. And how much space is required for this quick sort? It is always big O of log n. Next is binary search. So what is binary search? So we already discussed about linear search. So linear search is 10 elements will be given. I say key is equal to 100. That 100 will be compared with all the element until I get. I may get or not get. If I get, it is best. If I don't get, it is worst case. But binary search is something different. Even though it's search, but if I want to go for a binary search, my list should be sorted. So binary search also is an example for divide and conquer. Then why it is called binary search? So it involves, again it breaks the problem into sub-problems. As we know, divide only, it breaks. Then, here the binary search uses the divide and conquer strategy. So suppose you have taken sorted list as the input. What it does is, entire sorted array is the input. Then it will calculate the middle. So it is dividing, we have to calculate middle. How to calculate the middle? The middle is nothing but low plus high divide by 2. It is something like L plus H divide by 2, that is called M. So we are dividing. So once we divide, we get the middle element. Then what is low here? Low is the starting index. What is high? High is the last index. So in the binary search, we have conquer. What is conquer? Conquer is nothing but solving. So first we'll compare the middle element, that is ARR of mid. What is ARR? It is an array with the target value. If they are equal, then the target has been found. So what will the algorithm return? It returns the index of the mid. So suppose if it is 5, my A of mid is equal, then it will return the index, say 5. If suppose the target is less than AR of mid, meaning to say we have not found. So what happens? The search continues in the lower half of the array. So the search will be from low to mid minus 1. Next, again if the target is greater, first it may be equal, second it is lesser, third one is greater, such that the search continues in the upper half of the array. So it is not equal, so my mid will be mid plus 1. Next, the third is combine. So we have conquered, we have solved it, then we have to combine it. So the algorithm repeats divide and conquer steps such that the selected subarray until the target is found. Until you get the mid element, that is key is equal to that element, it will be keep on combining. Then what is the base case? So base case is reached when the subarray size becomes 0 or when the target is found. That is the base case. If the subarray size is 0, suppose my size will be 0 and the key element is not found. So what happens? That time the algorithm returns a special value -1 indicating that it is 0 or my key is not found. Next, coming to the algorithm, what are the steps to be followed? In the first step, we always know the index. The low will be set to 0 and the high to the length of the array. Say, if it is 0, then the array will be n minus 1. That is, if n is 5, what is 5 minus 1? It is 4. What in the case of step 2? So each time we have to compare with a condition. I always tell that my element should be more than 1. Only if more than 1 I can sort. Otherwise, the element it is sorted only. So first we check low is less than or equal to high. So it is something like low is less or equal to high. So low is less or equal to high. Then the condition. What is the condition? If the condition is true, then we have to calculate the mid. Mid has low plus high divided by 2. Say 0 plus, what is my high? High is 4. So 4 divided by 2 is 2. So this is the mid. Now we have to compare this A of mid is equal to target. Next, if A or array of mid equals to the target, then we had found the key element will return what? The mid. That is the index. What is the index? Index is 2 according to our example. Then suppose if AR of mid is less than the target, if suppose I am comparing the element that is less than the target, say my target is 20, my mid is 10. So 10 is less than 20. That time we have to set the low to mid plus 1, right? Then if array of mid is greater, each time we'll compare our array of mid with the target that is key. Again that time our high will changes. High means our variable will changes to mid minus 1. These are the two conditions. Depending on that, we have to set our low and high value. Again, if low is greater than high, what happens? Again, it will return a special value. Again, it is minus 1 to indicate the target is not present. So, binary search's target is key element. We'll see whether key element is found or not. So, what is the time complexity of binary search? So, time complexity in the best case is big O of 1. When this happens is, see I have 3 elements, 10, 20, 30. Okay, how to find out the mid? This is 0, this is 1, 2. So, mid is equal to the 0 plus 2, low plus high. 0 plus 2 is how much? 2. 2 divided by 2 is 1. Okay, suppose my key is equal to 20. So, what we discussed, we have to say mid, A of mid. What is A of mid? See what is A of 1 here? A of 1 is 20. Suppose my key is 20, I got A of mid is equal to key. I'll check a condition. So, 20 is equal to 20. I got, that is the best case. So, only one comparison I did. Immediately when I got my mid, when I compare with the A of mid, key is found. That is successful search. So, best case is big O of 1. When happens? When the target element is found at the middle. See, we got in the middle. That is best case. Then what about average case? Average cases will be if I don't get my key element in the middle. So, what is average case? The binary search performs very well on the average, repeatedly divides the search interval until the target is found. So, we have to keep on repeating what? Dividing until we get the key or until we get the target. So, the time complexity is again big O of log n. Since divide procedure is done, so we indicate with the log. Again, the worst case also similar. So, the worst case happens in two conditions. If my search element will be the last or I don't get the search element, that is big O of log n. So, we said that when the target is the last element or when the target is not in the array. So, that is the worst case. Even in the worst case, the binary search efficiency reduces the search space by half of it comparison. So, again the same complexity, that is big O of log n. So, what is the observation we have to keep in mind for the binary search? Is highly dependent on the input. See, binary search works only if it is sorted. If you don't give input in a sorted, if you give jumbled up numbers, binary search won't work. That time you have to go for what? Linear search. Means each one will compare and go. Binary search we divide. How to divide based on the sorted array? If it is not sorted, we don't get the key element only. So the logarithmic time complexity is big of log n. We have already discussed this. Next, what is the special note? See, while binary search is very efficient for searching the sorted array, it is important to note that initial sorting operation may add an extra cost. So since we are dividing and checking the middle element, again we are dividing, it will add an extra cost. So cost in terms of the complexity. So the space complexity of the binary search is big of 1. So why 1? We are taking the size of the input. Next is the binary tree. See, binary search, binary tree. But when we say tree, we have to consider this diagram. We don't take any array elements. We have to take a tree. So what is binary tree? And what is the difference between a tree and a binary tree? So binary tree, we consider this binary tree and the traversal and the properties of it. So we say binary tree T is defined as the finite set of nodes. It is not infinite. Finite means we can count. It is a finite set of nodes. Say this is the root. Here is a left subtree. Here is the right subtree. So binary tree is a tree T which has finite set of nodes, and that can be either empty. Empty means no nodes, say, and it consists of a root. So beginning we say this as a root. Okay. Then two disjoint binary tree TL and TR. For this we say TL, and for T right we say TR. So one thing we have to keep in mind, a binary tree can have no subtrees, or minimum it can have 2 children. If it is more than 2 children, then it cannot be called as binary. So we always say binary 0 and 1, say 2. If it is more than 2 children, then it is called a tree. Say if I take A, B, C. This can be a binary tree. Or even though this, and again I'll join with a D. It has 1 subtree. This is also a binary tree. It can have 0 or 2, maximum 2, not more than 2. If I say one more example, say X, it can join with Y, Z, or again starting with A. Here you have 3 of it, so it is not a binary tree. So that is the difference. So then we'll go to the binary tree approach. It is also a divide and conquer. So divide and conquer approach, and you have traversal. What is traversal? How you visit the nodes. That is, you have 3 types: pre-order, in-order, post-order. So when I say pre-order, that is, pre means what? The first node will come, that is root. Next, the left subtree, right subtree. If I say in order, in means in between. So if it is in between, so node will come in the middle and followed by left and right. Then what about post order? Post order means post means last. So here first left, right subtree, and then miss my node. See here you can find the difference. Pre-order first, in order root is middle, post order my node or root can be in the last. That is what is called traversal. Why we have to traverse? Such that we'll visit the tree root and its left subtree and the right subtree. Okay, next. So we discussed this pre-order traversal. Pre means the root is visited before the left and right subtree. First we have to visit which node? Root, to be called as pre-order. What about in order? In order means something in between. The root is visited after visiting left subtree, but before visiting the right subtree. Next, what is post order? Post already happened. So the root is visited after visiting left and the right subtree. If I say an example of a simple tree, A, B, C. See, if I want to be called as in order, So how it is in order? Left node right. What is left here? B. What is my node? A. What is my right? C. So this is called in order. Similarly, we can do for pre-order and post-order. We have to understand where the node should come. So this all completes your decrease and conquer and divide and conquer. So next session we'll discuss about the next unit. Until then, take care. Bye. Thank you.